we want to introduce another tool that would allow you to predict the stiffness of a spring if you know the coil diameter and the wire. You already know that if we were to plot the force displacement relationship for a linear spring, that we would get a straight line whose slope was k, and for any given displacement that we choose, delta, we know that we have pumped energy into the system, and the amount of energy we've stored in the system is stored elastic energy, so it can be recovered. And the magnitude of that energy, U, that is the stored elastic energy, is equal to 1/2 the base, that's delta, times the height, and that's going to be the force F that's associated with that delta. Well, we know for a linear spring that the force is going to be related to that displacement delta, and so that delta is simply going to be equal to F over K. This is going to seem a little bit silly what I'm going through here, but the stored energy then is going to be equal to 1/2 F squared over K. And if we take the partial derivative of that stored energy with respect to the force F, that is going to be equal to F over K, which goes right back to our definition of the linear spring. F over K is equal to the displacement. Castigliano understood that any elastic body, no matter how complicated the geometry, when loaded by a force, the force does work on that elastic body, and so long as it is everywhere elastic inside that body, then we are going to be storing that work as elastic strain energy. Castigliano said that if you could find that elastic strain energy and take the partial derivative of that elastic strain energy with respect to the force F, then you could get the displacement in the direction of the force F. So the partial of the stored elastic strain energy with respect to the applied load for an elastic body gives you the displacement under the load in the direction of the load. So that's something that we're going to want for a coil spring. Here's our section of coil spring where the wire diameter is lowercase d and the coil diameter is uppercase d. It turns out that when you compress this helical spring through an applied force F, we know that that force gives rise to both direct shear and torsional shear stresses. Those store energy in the system, and the magnitude of that stored energy can be expressed by this formula shown here. The first term in that formula is the torsional shear. The second term is the direct shear energy term. Now this is pretty straightforward and simple. It turns out that what you really want to do is integrate the stress times the strain over the entire volume of the sample. But we are assuming that there's no change in those stresses and strains as we move through the coils of the coil spring. And so this becomes a much simpler problem where we are simply going to integrate the torque that we are applying squared divided by twice the shear modulus and the polar moment of inertia. We're going to multiply that by the total length of the coils that are actively loaded. We do the same thing for the direct shear term, but instead of the polar moment of inertia, we're just using the cross-sectional area. The total length of the coils that are storing energy are simply going to be expressed as pi times capital D times the number of active coils. So pi times capital D, if you look at this diagram over here, is just the circumference of the coil diameter running through the centroid of those wires. N sub A is the number of coils that are actively loaded. We also know that the polar moment of inertia is going to be equal to pi d to the fourth over 32, and that the cross-sectional area is pi d squared over 4. We plug those three things up into this stored strain energy equation. We find that the total stored strain energy is simply going to be given by 4 times the force squared, the coil diameter cubed, times the number of active coils, divided by the shear modulus times the wire diameter to the fourth power, plus twice the force squared, times the coil diameter, times the number of active coils, divided by the wire diameter squared, and the shear modulus. If we take the partial derivative of that total energy with respect to the force F, that's going to give us the deflection of the helical coil spring in the direction of the applied force. And that is simply going to be equal to 8F d cubed times the number of active coils divided by the shear modulus times the wire diameter to the fourth power plus 4 times the applied force times the coil diameter times the number of active coils divided by the square of the wire diameter in the shear modulus. We can simplify this quite a bit, and we find that the elastic deflection of the coil spring in the direction of the load is equal to 8 times the coil diameter cubed times the number of active coils divided by the shear modulus and the wire diameter to the fourth power, all of that multiplied by 1 plus d squared, that's the wire diameter squared, divided by twice the coil diameter squared. This is can be simplified even further by recognizing that the spring index is the coil diameter divided by the wire diameter. And so the deflection term becomes equal to 8d cubed times the number of active coils divided by the shear modulus times the wire diameter to the fourth times 1 plus 1 over 2 times the square of the spring index. We can then note that I left the force out of those equations. I got to have the force in there in both of those equations. Sorry, because the deflection is related to that force. And then you know that the spring constant, because the force is related to K times Y, that the spring constant would simply be given by G, that's the shear modulus, times the fourth power of the wire diameter, divided by 8 times the coil diameter cubed times the number of active coils, and we divide all of that by 1 plus 1 over 2c squared. Well, this term, we usually just let it be equal to 1, and we get a much simpler relationship for an estimate of the spring stiffness as the shear modulus times the fourth power of the wire diameter divided by 8 times the coil diameter cubed times the number of active coils. This number of active coils, remember, it goes back to this simple relationship where we were using the simplified version of the stored energy equation. And we're just saying how many of those coils are carrying the stress that is represented in this equation. And so there's a huge number of estimates that are used to determine the number of active coils in a compressive helical coil spring. The first thing that you want to know is that we can terminate the spring in different ways. Shown here, the upper left, is a simple turned coil spring. Nothing has been done to the ends of the spring. This in the lower left is the last portion of the coil has been rotated, turned down so that it is flat. It is tangent to a plane that is perpendicular to the axis of the coil. We can also then grind that turned end flat. So when we turn the end flat, it's called squared. And in the upper right-hand corner, we see a ground squared flat end. And in the lower right-hand corner, we see a plane end that is simply ground flat. So it wasn't turned, it was simply ground flat. And so the number of active coils is going to be different depending upon how you make your springs. Table 10.1 out of the Shigley book allows you to calculate the number of active coils for each of these 4 representative helical compression coil springs shown in figure 10.2. You use these equations to sort out a number of things like what are the number of end coils, what are the total number of coils, you have to count those, what is the free length, meaning you aren't applying any load, how long is the spring end to end, what is the solid length when you completely compress the spring so that all the coils are touching each other, and then what is the pitch when the spring is allowed to be free. The pitch is the distance between adjacent coils in the the coil spring. So how far do you advance through one complete rotation around the helical coil spring?